Let's discuss the experiment number 7, the bullseye. The goal of this experiment is to release the ball from a specific height on an inclined ramp and make it accurately hit the target, which is the soup can. This activity aims to test the accuracy and precision of the setup by observing how the height, angle of the ramp, and the point of release affect the ball's motion from its target. Now, here are the list of required materials on doing this experiment. We need soup can, a DIY plumb line, a ruler or meter stick, a DIY ramp, a metal ball, and a stopwatch. Now, moving on to the steps of doing this experiment. The first step is arrange and stabilize the ramp by setting up a smooth, rigid surface with a vertical height of at least 30 cm. Secure it firmly using a clamps or tape to prevent any swaying or bending. Next, ensure the ramp has a level of horizontal section that at least 20 cm long so the steel ball exits horizontally. Step 2. Use a stopwatch to measure the ball's travel time from when it first reaches the tabletop level. After recording the time for each trial, we calculated the ball speed using B equals x over t by dividing the 20 cm distance by the time to find how fast it reached the tabletop. Now, for trial 1, the time recorded is 0.15 seconds. The distance of 20 cm, which is the measure of the horizontal section, is converted to 0.20 meters and divided by the time of 0.15 seconds. By dividing these values, we get a speed of 1.333 meters per second for trial 1. For trial 2, the time is 0.13 seconds. Using the same process as in trial 1, we get a speed of 1.538 meters per second. For trial 3, the time is 0.15 seconds, the same as in trial 1, resulting in a speed of 1.333 meters per second. Now that we've obtained the speed of each trial, let's get the average horizontal by adding the three speeds, which are the 1.333 meters per second, 1.538 meters per second, and 1.33 meters per second. Then dividing the sum by 3. This will give us an average horizontal speed of 1.401 meters per second. Now, moving on to step 3. Use a plumb line and string to measure the vertical distance or height from the ramp's lower end to the floor where the ball should land in the soup can. Moving on to step 4. Use the correct equation to calculate the time it takes for the ball to fall from the ramp to the can. Write the equation that relates the height to the time.
To start the solution, we will derive the vertical distance height equation to a time formula. Next is, we need to get the average time of the 3 runs by adding all the time that was made by the runs and divide it by 3. Since there are 3 runs in total. Next is, input all the values in the vertical distance height equation. And lastly, input all the values in the derived time formula. And with that, we will get the time it takes the ball to fall from the bottom end of the ramp and land in the can.
Step 5. In this step, we will predict the range of the steel ball by computing it using the formula for horizontal distance, x equals velocity times time. In this case, we have already computed the average time and horizontal speed, therefore we can directly substitute the values in the horizontal formula as a formula for the range. Therefore, range equals 1.401 meters per second times 0.143 seconds is equal to 0.200 meters or 20 centimeters.
Now, these are the recorded data based on this experiment. Now, moving on to the question and analysis of this experiment. First question: should the height of the can be taken into account when measuring the vertical distance? If so, make your measurements accordingly.
Yes, since the goal is for the ball to land inside the can, you need to measure from the bottom end of the ramp to the top rim of the can. So in order to get the height of the can, we need to subtract the height from the tabletop to floor from the height from tabletop to opening of the can.
In comparing our predicted range to the actual range of the steel ball, we calculated the percentage error, the formula of dividing the absolute value of the difference of the accepted value or the actual range of the steel ball and our predicted range to the accepted value, then multiplying the quotient of that to 100%. Hence, the absolute value of 47 centimeters minus 20 centimeters all over 47 centimeters times 100% is equal to the percentage error of 57.447%.
Now for third analysis, what may cause the ball to miss the target? The ball may miss the target due to several factors such as inaccurate measurements, uneven surface that can change its direction, incorrect release of the ball, wrong positioning from the target, or improper placement of the can. It may also fail to hit the target because of how it was held or released by the person or due to air resistance affecting the ball's path during its motion.
The role of the air resistance is in the name itself, to resist the steel ball's motion. With this being said, it is one of the factors that determines the steel ball's range. When it resists the motion, it reduces the steel ball's speed. Hence, this reduction of speed contributes as to where the steel ball will land, which in this case, into the empty can. Calculating the initial speed of a steel ball with a range of 47 centimeters or 0.47 meters and an average time of 0.143 seconds, we use the formula of horizontal motion, velocity equals range over time. Substituting the values, 0.47 meters over 0.143 seconds is equal to the steel ball's initial speed of 3.287 meters per second.
Now, for the reflection of this experiment. The bullseye experiment with 3 ball runs taught us that even small changes can affect the result. Slight differences in how we release the ball, small variation in the ramp's angle, or improper placement of the can cause the ball to miss the target. Factors like the ball's speed, air resistance, and the exact positioning of the can all influence the outcome. Repeating trials help us get more accurate data and identify consistent patterns. Overall, it was a fun way to learn about motion, practice precision, and understand how multiple variables interact in a simple experiment.